hear me?
Yes,
Just reviewing what I spoke in the last class. If you take a conductor, we are talking of static condition. If you take a rectangular slab of conductor and put it in an external uniform electric field E naught, then quickly the positive charges will go to the top surface, the negative charges will come to the bottom surface, and these two induced charge surfaces will in turn set up electric field called induced field. And the induced field setup will be sigma by epsilon naught. The sigma by epsilon naught will be exactly equal to the applied field E naught. Okay, or inside the body of the conductor, the net field will be the applied field plus the induced field. Now the applied field and the induced field will be in opposite in direction. You can see E naught is from top to bottom and the induced field is from bottom to the top, but magnitude wise they will be the same. Therefore, the net field inside will be 0. Okay, or in other words, you can say that the induced field is equal to sigma by epsilon naught. Now, based on that, let's quickly work out our problem. So, see here, you have a thin plate. Though it's thin, I have to draw and show you. So, I have a thin plate of copper placed in a uniform field. So, let me just draw this initially to show the uniform field. Okay, let E naught be the uniform field. Then what are you supposed to find out? And the value of the uniform field is given as 450 Newton per Coulomb. Okay, and it is perpendicular to the plate. So it's okay, our drawing is fine. Find the resulting surface charge density on the plates. Now if you see here, if you apply a field in this direction, where will the positive charges go, upward or downward? Or where will the negative charges flow?
Positive charge goes
upward. But then please remember it is a metal. So positive charges don't flow. It's only electrons which will flow. Okay, so what will happen? The electrons will all start experiencing a force opposite to the applied field. Therefore, in a short time, there will be an accumulation of negative charges on this place and a deficiency of negative charges on the upper plate. What is deficiency of negative charges? Deficiency of negative charges means positive. Okay, so there will be an accumulation of effective positive charge on the upper surface. Okay, let sigma be the charge density of both these plates. Therefore, as we have just seen, the induced charge will be equal to sigma by 2 epsilon naught because of the first plate, because of the positive plate, plus sigma by 2 epsilon naught because of the negative plate, which simply becomes sigma by epsilon naught. And we have seen that E naught and E prime modulus wise or magnitude wise, they will be equal. Only then the sum inside will become equal to 0. Okay, therefore, you can simply say that this is equal to sigma by epsilon naught. And what are you supposed to find out? You're supposed to find out what is the surface charge density on the plates. Okay, so from here you can see that sigma will be equal to E naught mod E naught into epsilon naught. Okay, so what is E naught? E naught is given as 450. And what is our epsilon naught? Epsilon naught is 8.85 into 10 to the power of minus 12. So if you take out a calculator and make a calculation, you should get sigma as 3.98 into 10 to the power of minus 9. What is the sigma? What is the sigma called? What does sigma stand for? Surface charge density. So what will be the unit? Charge by the area. So Coulomb per meter square. Okay. Now with this we are stopping our statics. Now we are going to dynamics. So when we talk of dynamics, I want you to remember something. So what is it I want you to recall? If I have a material like this, okay, if I call this as end as A, if I call this end as B, okay, and if I am going to apply a field, if I am going to apply an electric field like this, and if L is the length of this strip, then we have seen the relationship between potential difference and field. What is the relationship? E is equal to, anyone?
P by L.
V by L, or I can say delta V by L with a minus sign. That's what we have seen. Okay. Or from here you can see that it is going to be minus of VB minus VA divided by L. Okay. Or this is going to become VA minus VB divided by L, and this is E. Okay. Now, if the electric field is in this direction, from this equation, you can understand that there will be a potential difference between these two ends of this object. There is a potential difference between these two ends of the object. If the potential here is VA, the potential here is going to be VB, and you can quite simply see that VA is greater than VB. VA is greater than VB. Will you agree with me? I hope you understood this argument. If I have a strip of material of length L, and if I apply an electric field like this just means that I'm creating a potential difference between the ends A and B. What is the relationship between field and potential difference? Field is equal to minus delta V by L. Here I'm just writing, it's normally you write it as minus dV by dL or dV by dR. I know that difference is L. Okay, and I can see that it is minus, and what is this delta V? VB minus VA. Now let's remove this minus sign, it becomes VA minus VB by L. And if I'm assuming that the field in this direction, electric field is positive, then from that automatically it means that VA is greater than VB. That is, this end is at a higher potential. This is at a higher potential, and this end is at a lower potential. Okay? And at the same time, let us see what will happen to the charges. If I'm talking of electron, what will happen to the electron when I apply a field like this? Just now we did a problem, no? What will happen to the electron when you apply a field to the right? The electron
It experiences force towards the
opposite direction. It experiences a force in the opposite direction. So this is the way you actually create current. This is the way you create a current. Okay, so you also know by convention, that when you have a conductor, the direction of the flow of negative charges, if these are all negative charges, the direction of the flow of negative charges will be against the field that you are applying, will be against the direction of the field that you are applying. And by convention, current direction is taken as, this is the flow of the negative charges. This is the direction of the flow of negative charges. You are applying a field in the opposite direction. Therefore, this is our conductor, let us say. Let's say this is my copper plate. Okay, by applying a field E naught like this, I am making my electrons move in the opposite direction. And because I have provided a closed circuit, the electrons are all flowing in this direction as C. But by convention, the current direction is taken as the opposite direction. The current direction by convention is the opposite direction. So whenever we talk of a current flow, you must remember that the current flow will be in a direction opposite to the direction of the electrons. Okay, and you need a closed loop. What is the criteria for a conduction to take place? First thing is you need mobile charges. If I'm talking of a metal, the mobile charge will be electron, free electron. And then you need an EMF. I hope you know the expansion of EMF. What is EMF? What is EMF? Anyone? Electromotive force. There should be a force that's going to push the charges. The mobile charges should be pushed, because after all, current is moving charge. Current is moving charge. So you need a driving force or an EMF to push. So you can see here that that push is going to be provided by that field that you are applying. Or in other words, by applying a field, you are actually creating a potential difference. You're creating a potential difference between the two ends of the conductor, And just this example that I have shown you shows that the electron will flow from lower potential to higher potential. Look at the direction of the flow of the electron. You're finding that the electron is flowing from the lower potential to the higher potential or against the electric field. But what will be the direction of the current? Current will be from higher potential to lower potential. That is by convention. I hope you are now understanding how current actually flows. Is this clear to you? Let us follow this diagram, for example. The current is flowing like this, the current is flowing like this, and within the material, you see the current is going to flow like this. That means it is going in the direction of the applied field, or it is going from a higher potential to the lower potential. Okay? Whereas electrons will go from the low potential to the higher potential. Electrons will go from the lower potential to higher potential. Okay, and so as a result, what happens is here you are coming across a situation which is dissimilar to what you have seen in the previous class. In the previous class, we talked about something called electrostatic equilibrium. The charges, if at all they move, they are only going to move to some surfaces so that the electric field inside a conductor becomes zero. And this movement will be only for about 10 to the power of -9 seconds. But when you're talking of dynamics, this flow of charges will be continuous. Flow of charges will be continuous, and such a continuous flow of charge is called a current. Okay, and as mentioned, positive charges will move in the direction of the applied field from a higher to a lower potential. Negative charges will flow against that. And as a result of this flow, what happens is, within the body of the conductor, you are going to have free electrons. Free electrons will be there within the body of the conductor, or there is going to be a charge density, volume charge density within the, when I'm talking of this row here, I'm talking of volume charge density. There is a volume charge density within the conductor. Whereas when we talked about electrostatics, the excess charges went and sat on the surface. Inside, there was no excess charge. Rho was zero. Whereas here, rho is not zero. Similarly, in electrostatics, inside the body of the metal, at electrostatic equilibrium, electric field was zero. But here, that is not the case. There will be electric field, non-zero electric field, even inside the body of the conductor. So this is another difference. Then, in the last chapter, though I didn't teach you that chapter, we have seen that the entire conductor will be at the same potential. Inside and outside, the potential will be the same. But that is not what is happening here. In the case of electrostatics, there is a potential difference between any 2 points. There is a potential difference between any 2 points within which there is going to be a flow of charges. Okay, so delta V is not equal to 0. Is this page understood? Is this page understood? Here I am shouting for hours. You people cannot open your mouth and say yes or no.
Ma'am, could you repeat the last point?
This last point. Okay. See, if I am talking of, I think I should just discuss electrostatics here. When I talked about electrostatics, I said, if I put some charges on a metal, or even if I don't put some extra charge on a metal, what will happen if there is an external electric field E0? Then we have seen that charges will flow and sit on the surface so that the electric field inside will become zero. After that, no movement of charges will be there. And last class, we also discussed that E equal to minus dV by dr or dV by dl. Here, this just means distance. Okay. Now, if electric field is zero, this implies that V is the same everywhere. The same everywhere. Okay. This is in electrostatics. So in electrostatics, no excess charge inside, which means rho is zero. And excess charges will go and sit on the surface. Electric field inside becomes zero. That means there is no potential difference between any point of the conductor. Everywhere the potential is the same. Is this understood?
Yes, sir.
Right. Now let's just go back here. Whereas here, what is happening? Because of the electric field, the continuous electric field that you're applying, charges are flowing, and you have provided a closed path. You have provided a closed path. Because you have provided a closed path, what is happening? The electrons which are moving are able to move out of the conductor, go through the circuit, and then come back like this. So there is a closed loop. And the direction in which the electron flows will be against E naught. Okay? And it will be from a lower potential to a higher potential. Whereas current, by definition, is opposite to the flow of electrons. So current will be flowing from a higher potential to a lower potential. Okay, and because this flow is continuously there, it is not electrostatics. So that means even within a wire or within a conductor, charges are flowing. Mobile charges are there. Therefore, charge density is not zero, rho is not zero. Okay, and because there is no electrostatic equilibrium, electric field is also not zero. Because I've shown you there is a potential difference. There is a potential difference, that means there is an electric field inside. Okay, and because there is an electric field, the potential difference is also there. So the entire body is not at the same potential. Did you understand this?
Yes, yes.
Right. Okay, now this is how current flows, and this is called dynamic condition. Now let's go to the definition of what is a current. Okay, so what is current? Current is the rate at which charge will flow. The rate at which charge will flow. So if I'm going to talk about a conductor, sorry, look at my bad drawing. If I talk about a conductor, okay, let's say the conducting wire is like this long, and this entire, it's like a tube, okay, and I'm taking a cross section of that wire. Let the area of the cross section be A. Okay, so if I could see charges, if it was possible for me to see charges, what would I see? I would see electrons cutting through that area of cross section of this wire and then going in this direction, which means current is in the opposite direction. If A is the area of cross section, and if the current is flowing uniformly through this entire area, or if the number of electrons cutting through is uniform for this entire area of cross section, if I say this is my wire, then I'm cutting this and I'm talking about an area. So throughout this area, if there is going to be a flow of charges, then my current is how many charges flow, what is the charge flowing or crossing this area in 1 second. The amount of charge crossing that area in 1 second. Or mathematically, you write it as I equal to dq by dt. Is this understood? And what is the unit of current? What is the unit of current? Ampere. Unit of current is ampere. And you can see that ampere, what is ampere? Ampere is simply going to be coulomb per second. It's just coulomb per second. Now, I don't have to do this dq by dt if it is a constant current. If it's a constant current at any given time, if I say that 10 coulomb is crossing that surface, 10 coulomb is what is going to cross in the first second, 10 coulomb will cross in the second, third second, anytime it's going to be 10 coulomb. Therefore, I need not write dq by dt. I need not take a small time interval. I can simply say the total charge crossing in a time t. So q by t. And please remember, this is a scalar quantity. It doesn't have direction. One thing, it doesn't have direction. Okay, it is scalar because there is no direction. That is one reason. Some of you will ask, ma'am, current has a direction. Okay, so I need to amplify here. You cannot talk of components. No components. For any vector, you can talk about, if I have a vector like this, I can talk about a component in this direction, a component in this direction. But you cannot talk about components for current. Okay, if you have a wire like that, it will be going from high to low potential. That's all right. That is a direction, nothing beyond that. But you cannot talk about the amount of charge flowing along the x direction, y direction, z direction. Such components you cannot say. Therefore, current is a scalar quantity. Okay, now we have just seen that I equal to dq by dt. This is the most general equation. So now let us say dq will be equal to I dt. dq is equal to I dt. Let's say I'm interested in finding out how much charge went across that cross section in, let us say, 10 seconds. In a time t equal to 10 seconds, how much charge actually crossed that cross-sectional area? If I'm interested in finding out, then what should I do? I just need to differentiate this from time equal to 0 to time t equal to 10 seconds. So if I do that, I will get integral I dt. And on the left-hand side, what will I get? I will get q. Or I will get q equal to integral I dt. So this is the equation that's going to give me the amount of charge that crosses a cross-section of the wire, a cross-section of the conductor in a time t seconds. Okay, and please remember, current is not a vector, but you need to talk about what is the direction in which the current is flowing. The current flow direction is taken as the direction of the electric field in that part of the conductor. So if I'm going to talk about a conductor, if I'm going to talk about a conductor like this, okay, it's a long conductor. I'm not talking about the rest of the circuit. Okay. And if I'm going to talk about a current that is flowing in this direction, this just means that inside the body of this conductor, there is an electric field in the same direction. Current is always taken as parallel to electric field. Okay. And current is taken as a direction of the flow of positive charge. So you will ask, ma'am, you said positive charge doesn't flow in a metal. Yes. Positive charge doesn't flow in a metal. It is only electrons that flow. Electrons will flow in the opposite direction. Therefore, it is assumed that the positive charge, if it had moved, would be going in the opposite direction. So that's the direction of current. Is this clear?
Yes, sir.
Right. So now we have talked about a quantity called current, and we have talked about a quantity that is a scalar. But then we love to work with vectors. We love to work with vectors because after all, field is a vector. Electric field is a vector. So I should be able to talk about the current flow and the electric field because after all, the electric field is responsible for the current. Okay. So if I have to write an equation connecting these two fellows, I need to somehow talk about a vector quantity representing the flow of charges. And that quantity which represents the flow of charges is called the current density. And please remember, current density is a vector quantity. Once again, I repeat, current flow is there because you applied an electric field. An electric field is a vector quantity. So mathematically, if I have to relate the current flow to the cause, which is the electric field, I should be able to represent the current flow also in terms of a vector quantity. Only then mathematically I can write an equation. So that quantity, that vector quantity that represents the flow of charges is called the current density. And how do you represent current density? The current density is simply di by dA. Or I will simply first say current density equal to I by A. What is A? A is the area of cross section of this conductor. This is my conductor, which is having a circular cross section. Okay. Now, I is the total current that is flowing. I is the total current that is flowing, and it is flowing in this direction. Okay. Current divided by area of cross section is your current density. Okay. Now, what will be the unit? You tell me. What will be the unit? Look at these quantities and tell me the unit. What's the unit of current?
Ampere per.
Ampere per. And what is the unit of area? Area is meter square. So ampere per meter square is the unit. Okay. Okay. Now, here I have made an assumption that the flow of charges will be uniform through this entire cross section. It's a uniform flow. Then I can write J is equal to I by A. Okay, and I said vector. I've been talking about a vector. So what is this vector? Let us see. Okay, now you look at this. You just do a cross multiplication. Then I can be written as J dot A. Current can be written as J dot A, where I am treating J and A as vectors. J and A as vectors. In Coulomb's, in the chapter, what was that? Gauss law. In the chapter Gauss law itself, we have seen how area can be treated as a vector. So we're going to do the same thing here. Okay, J is a vector, area is also a vector. Let us see the direction of that. J will have the direction of current. J vector will have the direction of current, and A vector will be perpendicular to A. A vector will be perpendicular to the area of cross section, and it will be parallel to J. I hope you're understanding this. If this is my area of cross section, let's say this is my area of cross section, and let's say my current is flowing in the downward direction. Are you able to see this pen?
Yes, ma'am.
If this is the area of cross section of my wire, and let's say current is flowing in the downward direction, that means the electron is going in the upward direction. Then I take my J as parallel to I, and then I take my area as, let us say this is 2 millimeters square. Then my area is 2 millimeters square with a direction parallel to my J. So that's how I treat my area vector. Therefore, J dot A will always be equal to JA. J dot A will always be equal to JA because they are parallel. So cos of 0, therefore 1. So it will be J into A. And please remember, this is true as long as the current is uniform. What is the meaning of uniform? I'm talking about the area of cross section, and if I say that I take a small 1 micrometer cross section, a small part of that area, the amount of charge that is flowing should be equal to another such area that I'm taking, another such area. That means if I take tiny bits of this area of cross section, the charge that is flowing through each of these bits should be the same. Then I say that charge flow is uniform or current is uniform. Understood this? What's the meaning of uniform current? What I mean is, I have my total area A. I have my total area A, which I can divide into number of small areas. I can divide it into number of small areas. Each, I call it dA, let us say. Then the amount of current flowing through each of these should be the same. Then I say that the amount of charge flowing through each of these areas is the same, means then I say that the current flow for this entire cross section is uniform. So if that is the case only, this definition holds good. I equal to J dot A holds good only in that case. And J equal to I by A holds good only in that case. Okay. Now you will ask, ma'am, can you have a situation where that is not true? Yes, it can happen. I'll explain. Let's say I have a material. Let's say it's copper. Okay. Copper can oxidize, you know. Okay. Or let me say I added some impurity and I have changed the composition of this copper wire. Some areas the composition is something, some areas it is pure copper. Okay, then what happens is conductivity will be different. Different areas will allow different amount of currents to pass. So that means it is not uniform current. It is not a uniform current flow. So if it is not a uniform current flow, then what should you do? If it is not a uniform current flow, then what you should do is find the current DI through each of these small areas. Each of these small areas dA, you find out what is the current. Let that current be DI. And if I want the current through this entire cross-sectional area, then I just do integral DI equal to integral J dot dA. Are you following this? And here what happens is J will be defined as DI by dA. I'm talking about a small area dA. I'm talking about the small current DI going through that area. And I'm going to integrate it for this entire cross section. Then I get my current density. or I get the total current if I'm going to take this and then do di equal to j dot dA. Then I do an integration. Then I get I, net current. Did you follow this?
Yes, yes.
Right. And again, here also area vector and j vector are taken as parallel and they are parallel to the current direction. Okay. Now you look at this. Do you remember your flux, definition of flux, electric flux? Anyone remembers what is electric flux? Gauss law you just completed. Electric flux was?
E dot A.
E dot dA. And it is E dot A if it is a uniform field for the entire surface. And okay, but otherwise you will write it as integral E dot dA. Now compare what I have just written here. Compare what I have just written here to what I have written here. So what I have written at the bottom is a flux of the electric field. By that logic, what is this? It is a flux of integral j dot dA is a flux of
Current density.
Current density. Flux of current density is current. Okay, flux of current density is the current through the cross-sectional area. The book doesn't talk about it very explicitly. I just thought I will mention it here. You people can note it down. Okay. Okay. So now, yeah. So now we have been introduced to a term called J, and we have been introduced to a electric field. J is, after all, talking about current flow only, but then it is current per unit area, and then it is also a vector. So now I'm able to relate to, next what we are going to do is we are going to relate this J and the electric field that cause this J. Both are vectors. And incidentally, J and E are also parallel to each other. It's going to be easy to connect these two quantities. You're understanding why certain terminologies have come into physics? I'm just trying to talk about that chronology by explaining this. Otherwise, I could simply just define J is equal to I by A. But I'm just trying to explain why it was necessary to go through this process. Okay, so now we will be in a short time seeing the relationship between J and E. But before that, let us again go back to definition of current. Current is a flow of charges. And if the current, so first of all, you have to produce a potential difference between these two ends. Okay. And then let the length of the conductor that you conduct, or let us take a piece of the conductor of length L. So there is a potential difference between these two ends. And because of the potential, this potential difference came because of the field that you have applied. Okay. And as a result, what is going to happen? The current will be flowing in this direction, or the current density will be flowing in this direction. Okay. And the actual charge flow, the electrons will be flowing in the opposite. Sorry, what did I do? One sec. Okay, you can see here the electric field is in this direction. Okay, that means there is a potential difference between these 2 points. And because of this potential difference, your current is going to be in this direction, parallel to E, or your J vector is also going to be in this direction, parallel to E. But what is the real motion happening? The real motion is that of an electron moving in the opposite direction. The electrons are going to move in the opposite direction. Okay, and if they are moving, they have to have some velocity. Now the velocity, the average velocity with which the electrons will flow in a direction opposite to the current is called Vd, or the drift velocity. It's called the drift velocity. The electrons will be drifting in a direction opposite to the current. And this average velocity with which they are drifting is called the drift velocity. So let Vd be the drift velocity. Okay. And a few minutes back, we said that there is a potential difference between these two ends, and we call that potential difference as delta V. Okay, and now we can relate electric field, this potential difference, and the length. Instead of writing delta V, let's say it is V. Okay, so E is equal to minus V by L is the relationship between the electric field, potential difference, and the length of the conductor. Okay, now what we are going to do is, if Vd is the average speed with which the electron is flowing, okay, now an electron which is here has to travel a distance L to cross a cross section. If I am going to talk about a cross section here, this electron to go out should be traveling a distance L, and let the time t be the time taken for it to travel this distance L. Then how do you relate the drift velocity t and L? Are you following what I'm saying? I'm taking a length L of the conductor. I'm talking about an electron at this end. If it has to cross this cross section, it has to first of all travel a distance L, capital L. Let it travel in a time t. Then what is the relationship between drift velocity L and t? Velocity is normally distance traveled by time. Okay, or in other words, now I am able to see that it will take a time equal to L by Vd to cross this distance. This point is clear? Okay, now what we do is, I'm going to come to a very important expression. So now what we are going to do is, we talked about one such electron. We just talked about one such electron. Now we are going to talk about all the electrons lying from here to here. All the electrons lying from here to here. Okay, what will be the volume of this? If A is the area of cross section and if L is the length, what is the volume? Volume of that part of the conductor is A into L. Okay, now let us say that the N is the number density of electrons, number density of free electrons. Number density means the number of electrons, number of free electrons available per meter cube of the material. That is fixed for any given element. For any given element, it is fixed. Let small n be the number density of free electrons. Number density means number of electrons, free electrons per meter cube of that given metal. Okay. Now, let N be the number density. And the volume you have is A into L. Okay. Then, what will be the number of free electrons available within this volume? What will be the number of electrons available within this volume? Let it be capital N. So, how do you relate small n, A and L? Small n is a number per meter cube. What is the number in a volume AL?
Small n.
Small n into A into L. Small n into A into L is the number of electrons in the volume. Okay. Now, what is the current? Current is the charge going across this area in a time t. Okay, so now let us try to get the expression. The charge crossing, not the number of electrons, it is the charge cutting across this area per unit time. Okay, so what we will do is, let us take t as the time interval, okay, and then write what is the total charge that will cross. What will be the total charge that will cross? All the charges present inside this volume will cross this area in a time t. Because in the previous page, I told you how the last fellow sitting at this end will also be able to cross because his velocity, time, and L are related. Okay, so this fellow will also be able to reach there, which means all other guys in front will also cross. So I can safely assume that this entire small n AL will cross. Okay, and let each of them carry a charge E. E is the charge of the electron. So what is the total charge that will be crossing? It will be NaL, that is the number, into the charge of each of the electron divided by time will be the current. Did you follow this? How many electrons will cross? The number of electrons that will cross is small n into A into L, that you all agreed. How much charge will it carry? Each will carry a charge E equal to 1.6 into 10 to the power of minus 19 coulomb with a minus sign. So NaL will carry NaL into the charge of one electron. So that will be the total charge that will cross in a time t. Therefore, by the definition of current, current will be NaLE by t. Next, what you do is, let us assume that it is a uniform flow of charge. Therefore, the current density will be current divided by area, we just saw, or total charge divided by time, or I will write current divided by area. Current we have seen is NeAL divided by area. I'm sorry, divided by time. And then of course you have an area. This area and area will get cancelled out. I hope I understood this step. J equal to current by area. Current you already got here. Substitute it here. When you substitute, area and area will get cancelled out. Okay, so you'll be left with NeL by T. And in the previous page, you have seen that drift velocity is L by T. Drift velocity is L by T. Therefore, instead of L by T, you just put drift velocity Vt. Or you're now getting a relationship between J and the drift velocity, the current density and the drift velocity. And please remember, velocity is a vector. Velocity is a vector. We are talking of the velocity of the electron. Electron is flowing in a direction opposite to the current density. Therefore, vectorially, if I have to write it, I will write J equal to minus NeVt. Why this minus sign?
Electrons flow current.
Vd direction is opposite to the J direction. So this is the relationship between the number density of carriers available, then charge of each electron, and the drift velocity. So this itself shows that any material which is going to have sufficient number of free electrons, or if it has a large number density of free electrons, only such a material can be a good conductor. If you don't have sufficient N, then it can be a semiconductor, and if N is going to be still smaller, it will be a dielectric. Okay, now we have talked about a metal. Okay, now let me just talk about, let us say, a liquid, electrolytic solution of NaCl. Okay, let's say the current is in this direction. Current density is in this direction. Okay, so now what are the carriers which are there now? What will be the carriers now? Is it electron? In Na plus Cl minus, what will carry current, you think?
Cl minus.
Cl minus and Na plus, both can move. It's a solution. Okay, it's an electrolytic solution. So what happens is, these positive Na plus will all flow in this direction, and the negative Cl will flow in the opposite direction. So both will conduct. Both will conduct. So this equation J is equal to minus NeVd applies only to metals. If I'm going to talk about an electrolytic solution, then I have to take two J's. One J coming because of the positive flow and one because of the negative flow. And when you're talking about the positive flow, that minus sign will not be there. And again, drift velocity also may not be the same for Na plus and Cl minus. Whichever is heavier may be having a smaller drift. Okay, now that you have understood all this, now solve some mathematical equation we have seen. Now, what is the typical value of drift velocity is the next question to answer. What's the typical value of the drift velocity for a metal? Okay, for that, I need to quickly talk about something called average thermal velocity. What happens if I take a block of metal and let's say I'm able to blow it up and look at the atoms? What I will be seeing is lattice. Lattice means I will see the positive ions fixed to their position at regular interval. Copper, for example, Cu plus ion will be sitting in regular interval, okay? And let's say each of them is going to donate one free electron. These free electrons will not be bound to the atoms. It will not be bound to the ions. They will be drifting around. They will be moving around. That's why they are called free electrons. And these things which are sitting in their fixed places are sitting in what is called lattice positions. They are sitting in their lattice positions, and these electrons are actually free electrons which are able to move around. And what happens normally is, you're talking of temperatures, even room temperature is a big temperature. It's a lot of thermal energy these electrons will get. So what will happen to these electrons normally? You're not applying any electric field, you're not applying a voltage, nothing. Okay, so what will happen to these free electrons, these free electrons will be in a state of random motion. These free electrons will be in a state of random motion. They will be moving in all directions like this. And in the process, what happens is they will be hitting against another electron or the lattice, and then they will change direction. So this keeps on happening. This random thermal motion keeps on happening. And because of this thermal motion will be there, but it is so random that effectively no charge will be flowing out. All the charges will be confined there only, within that area or volume only, but they will be randomly moving. And they will be moving because of thermal energy, and the energy with which, the speed with which they will be moving will be 10 to the power of 6 meter per second. Is 10 to the power of 6 meter per second a large velocity?
Yes, yes.
Very large. See, every time I like to give some examples, those things that should remain in your mind. My dad, he used to use that very famous phrase in my childhood. If I'm aimlessly roaming around the house doing nothing, I'm supposed to study, I would go to the kitchen, I'll go see what my mother is doing, then I'll go out, just walk around aimlessly. He used to say, why are you roaming around like a shanty dog? Do you know what's a shanty? You know what's a shanty? Shandy, the market where you sell vegetables, this Raitu Bazaar kind of things. Yes or no? Are you even listening? You know what's a shandy, I suppose? The nearest I can tell is the Raitu Bazaar. Have you seen Raitu Bazaars?
Yes, ma'am.
Right. Those days, now dogs don't enter the Raitu Bazaar. They have all those passages blocked. They don't enter. But those days, dogs will enter. And if you see, the dog is the busiest person in that market. Dogs will be the busiest fellows. They'll be running inside all over the place. They'll be running from stall to stall. But are they buying anything? Nothing. They're not buying anything, but they have a lot of energy. They'll be running around. Okay. So if somebody is simply running for no cause, that is called a shanty dog. So remember, these electrons are like shanty dog. They have a lot of energy. They're simply going to be running up and down, okay, randomly. But effectively, they have not bought anything. They have not transported current. Okay, so that is what is thermal velocity. That is the average thermal velocity with which these electrons will be randomly moving, hitting people, and then hitting other electrons. They will be hitting other lattices, but then they'll keep changing direction. They'll just keep dancing within that volume. So this speed is 10 to the power of 6 meter per second, and this energy is coming from thermal. That is the room temperature or any temperature above that. In comparison, what will be the drift velocity of the electron? Drift velocity is a purposeful movement. It's a purposeful movement happening in the direction opposite to the applied field. So what will be that speed? That we'll see in the next class. Guys, on Monday, I just put some message there. All of you, please listen. I need to take one special class on Tuesday. Tuesday, people are having EG class from 9:30 to 11:30. At 11:30, I will take a class. You know, I rarely take a special class. So please come for a class. That way, by Tuesday, this chapter will be over. Okay, so our point that we will start with will be what is typically the drift velocity. Drift velocity is not the same as random thermal velocity. Any doubts?
No, ma'am.
Okay. So please study, and I also left some messages for you people in the chat. We are having the next we are going to have is a quiz 2. Quiz 2 will be on 2 chapters, 28 and 29. That's the reason why I want to finish 29 fast. Otherwise, I can keep on teaching, but then you won't get time to prepare. Okay, then you have a test 2. Test 2 will have 28, 29, and 30. 3 chapters are there. Next, there is an assignment 2. For assignment 2 also, we have actually included these 3 chapters. Look at the handout for the date. And then there is also a makeup examination for students who have missed the test 1. All these 4 activities have to happen in this next 2 weeks. So please buck up, study, and be prepared. Okay?
Okay, ma'am.
Yeah. Okay then. Good day. You can leave.
Thank you, ma'am.
Yeah.
Thank you, ma'am.